Hi, Doc Revis here. In this video, I'd like to show you how to consider percent compositions in doing molar mass and molecular formula calculations that involve gas laws. We show you here some equations for the gas laws. We have Boyle's, Charles, Gay-Lussac's, Avogadro combined gas law. These 5 gas laws are comparative. In other words, you'll always have a starting condition and a final condition. You'll have one set of conditions versus a second set of conditions. So, Boyle's, Charles, Gay-Lussac's, Avogadro combined will always be comparative. That's one way to know you're using one of these laws. Then we have the ideal gas law. PV equals nRT. We also have an example here of a modification of the ideal gas law, which allows you to calculate mass or molar mass. Then we have density formulas here for relating them to ideal gas laws. And we also have a molar mass when we have density. We also note in this one standard conditions. Temperature is 0 C, but we always report temperature in Kelvin, K. Then standard pressure is 1 atmosphere or 760 millimeters of mercury. And an STP is important to note that 1 mole equals 22.4 liters. We have a conversion of 1 atmosphere to 760 millimeters of mercury or 760 torr. Note that when we use the ideal gas law equation, there are universal gas constants and we have to match those to the units. That is an important thing to remember, that matching the R universal gas constant to the rest of the units in the problem is very important. Let me show you how to do this by working a problem. And here's the problem. Chemical analysis of a gaseous compound show that it contains 33.0% silicon and 67.0% fluorine by mass. At 35 C, 0.210 liters of the compound exerts a pressure of 1.7 atmosphere. If the mass of 0.210 liters of the compound was 2.38 grams, calculate the molecular formula of the compound. Let's talk about how we approach this problem. To carry out a problem like this, you want to think about it in 3 parts. First, find the empirical formula. Second, get to the molar mass. And third, then obtain your molecular formula. Part 1. Use the percent composition of silicon and fluorine to find the empirical formula. Note, percents can be assumed to be grams when the sum of the values equals 100 or 1. In this case, it equals 100. Therefore, we'll assume that 33.0% silicon is 33.0 grams silicon, and 67.0% fluorine is 67.0 grams of fluorine. Part 2. Use gas law formulas to calculate the molar mass. Then Part 3. Use the ratio of molar mass to the empirical mass to determine the molecular formula. So let's proceed. First, by finding the empirical formula. To find the empirical formula, we know that we must have moles. If we are to find any empirical formulas, we must get our grams converted to moles. Therefore, we start with the moles of silicon. The moles of silicon will equal 33.0 grams of silicon. We do a dimensional analysis, a conversion of grams to moles using 28.09 grams of silicon per 1 mole silicon, and we obtain 1.17 mole of silicon. We likewise calculate the moles of fluorine starting with 67.0 grams. We do a dimensional analysis to convert this using 19.0 gram per mole of fluorine, which is the molar mass of fluorine, which equals 3.53 moles of fluorine. We then set up the ratio of the larger value divided by the smaller value. And for silicon, we find that we have 1 unit of silicon. And for fluorine, we find that we have 3 units of fluorine. Therefore, our empirical formula is SiF3. Next, let's determine the molar mass. We will determine the molar mass by using the ideal gas law equation, where we will get the moles, and we will use those moles and the number of grams to determine the molar mass. So, we are given 2.38 grams, and we know the ideal gas law is PV equals nRT. We rearrange the ideal gas law equation to show that N equals pressure times volume divided by RT, with R as the universal gas constant. We choose it according to the units we need for the problem. So we note we have atmosphere in the pressure, therefore we're going to need atmosphere in the R. We also note that temperature should always be in Kelvin. Therefore, we put in all the values, all the units are checked, and we obtain 0.0141 moles of this gas. We then take a standard gram per mole, mass per mole, where we take the mass at 2.38 grams divided by the moles, and we obtain 169 gram per mole as the molar mass of this gaseous compound. We did this by using the ideal gas law to solve for N, and we took the known grams, the given grams of the mass of this compound, and we did gram per mole, and we obtained the correct value. To determine the molecular formula, step 3 or part 3, use the ratio of the molar mass to the empirical formula to determine the molecular formula. We note that the empirical formula, SiF3, has a empirical mass of 85.09 grams. We take that ratio of the molar mass, which we've already obtained, of approximately 169 grams, divided by the 85.0 grams, and we get a value of 2 as the ratio of the molar mass to empirical mass, which means now we will multiply our empirical formula times the value of 2, and we obtain SiF3 times 2, which is Si2F6 as the molecular formula. So there you have it. How to calculate molecular formula and molar mass using percent compositions and gas law equations.